Our story begins not with a bang, but with a whisper. A faint point of light, captured by a telescope in the darkness of a Chilean night. July 1st, 2025. The Atlas Survey Telescope in Rio Hurtado, its robotic eye scanning the heavens for threats, for asteroids that might one day strike Earth, detected something unusual, something that should not have been there. A moving point of light, too fast, too bright, travelling in a direction that made no sense for any object born in our solar system. At first, it was just a number in a database, a coordinate, a brightness measurement. But within hours, as more observations came in, as astronomers around the world turned their instruments toward this mysterious visitor, the realization began to dawn. This was not one of ours. This was something from beyond. An interloper, a stranger, an ambassador from the vast darkness between the stars. They named it 3I Atlas. The I stands for interstellar. The 3 because it is the third confirmed visitor from beyond our solar system. Before it came Oumuamua in 2017, the strange cigar-shaped object that sparked 1,000 theories. Then 2I Borisov in 2019, a more conventional comet, yet still profoundly alien. And now this, 3I Atlas, racing through our cosmic neighbourhood at 137,000 miles per hour, faster than any natural object we have ever tracked, on a trajectory that will bring it close to the Sun and then carry it away forever, back into the infinite void from which it came. But there is something about 3I Atlas that is different from its predecessors, something that has caused NASA, in quiet rooms far from public view, to mobilize resources, to redirect spacecraft, to assemble teams of scientists who speak in hushed voices about possibilities that cannot yet be shared with the world. There is something about this visitor that demands investigation, that whispers of secrets, of knowledge that could change everything we think we know about the universe and our place in it. This is not a story about a comet. This is a story about a moment in human history when we realized with certainty that we are not alone in the cosmos. Not because we detected a radio signal from a distant civilization, not because we found ruins on Mars or microbes in the ice of Europa, but because an object came to us from impossibly far away, carrying within it the chemistry of another world, the fingerprints of another star system, and perhaps, just perhaps, evidence of design. Let us begin this journey not with speculation, but with humility. Let us acknowledge that what we are about to explore exists at the very edge of our knowledge, in the territory where science meets wonder, where facts meet mystery, where the careful measurements of instruments collide with the ancient human impulse to ask, are we alone? And if we're not, what does it mean when they come to visit? The discovery of 3I Atlas was announced to the world on July 2nd, 2025. The press releases were measured, scientific, careful. Interstellar object detected, poses no threat to Earth, offers unique opportunity for study. But behind the scenes, in the secure facilities of NASA, the European Space Agency, and other space organisations around the world, a different conversation was happening. This was not just another comet. This was an opportunity that would not come again in our lifetimes. An object from another star system, passing through our solar neighbourhood, close enough to observe, to study, to understand. And the window of opportunity was closing. 3I Atlas would reach its closest approach to the Sun on October 30th, 2025, and then it would begin its long journey back into interstellar space. By early 2026, it would be too far, too faint, too fast to study effectively. The clock was ticking, and so a decision was made. A mission unlike any NASA had ever attempted. Not a mission to send a spacecraft to intercept the comet. That would take years of preparation and more fuel than any rocket could carry for such a fast-moving target. But a mission to coordinate every available instrument, every telescope, every spacecraft that could possibly glimpse this visitor, to extract every possible piece of information before it vanished forever. A mission to answer the questions that had haunted humanity since we first realized we live in a universe of stars. What is it made of? Where did it come from? How old is it? And most provocatively, most dangerously, most thrillingly, is it natural? This is the story of that mission. The secret observations, the hurried consultations, the middle-of-the-night phone calls between scientists. The mounting data that suggested 3I Atlas was not just any comet, but something extraordinary. The quiet certainty growing in the scientific community that this object held answers to questions we had not even known to ask. But to understand why 3I Atlas matters, why it has captured the attention of the world's greatest minds, why it represents a turning point in human history, we must first understand what it is, where it came from, and what makes it so different from anything we have ever seen before. Let us step back from the immediate excitement of discovery and ask the foundational question: what is an interstellar object, and why should we care? To comprehend the significance of 3I Atlas, we must first grasp a profound truth about the universe. Space is not empty. Between the stars, in the vast gulfs that separate solar system from solar system, there are objects, wanderers, exiles, worlds that were cast out from their home systems, or that formed in the darkness between stars, or that are fragments of planetary collisions long ago, drifting forever in the cosmic void. For billions of years, these objects have travelled through space, moving at speeds that would make our fastest rockets seem like snails. They have passed through nebulae, felt the gravitational tug of black holes, witnessed supernovae from the front row. They are time capsules carrying within them the chemical signature of their birthplace, unchanged by time, preserved in the freezer of deep space where temperatures hover just a few degrees above absolute zero. Our solar system is one island in a vast ocean, and like any island, it occasionally receives visitors from distant shores. Most of these visitors are too small to detect, or they pass too far away or too quickly for our instruments to notice. But every now and then, one comes close enough, bright enough, slow enough for us to see it, to say, "Wait, that does not belong here, that is not one of ours." The first confirmed interstellar visitor was Oumuamua, discovered on October 19, 2017, by the Pan-STARRS telescope in Hawaii. The name is Hawaiian, meaning scout, or first distant messenger, and it was indeed a messenger, though its message was cryptic. Oumuamua was like nothing we had ever seen. It was elongated, shaped like a cigar or perhaps a pancake, tumbling end over end as it hurtled past the sun. It reflected light strangely. It accelerated slightly as it left the solar system, pushed by some force that we could not fully explain. Some scientists suggested it was simply outgassing, like a comet, releasing jets of vapour that pushed it like a rocket. But Oumuamua showed no visible coma, no tail of gas and dust like normal comets display. This led to more exotic theories. Was it a shard of a planet torn apart by gravitational forces? Was it an iceberg of hydrogen, frozen in the depths of space? Or, as one Harvard astronomer provocatively suggested, could it be artificial, a probe or a sail sent by an alien civilization? We will never know. Oumuamua came and went too quickly. By the time we realized what it was already leaving. We had no spacecraft in position to intercept it, no time to plan a mission. We could only watch, measure, and wonder. It left us with more questions than answers, a tantalizing glimpse of the interstellar ocean that surrounds us. Then came 2 Soldas Borisov, discovered on August 30, 2019, by amateur astronomer Gennady Borisov from Crimea. This object was, in many ways, the opposite of Oumuamua. It looked exactly like a comet. It had a bright coma, a long tail, and it behaved predictably as it approached the sun. Its chemistry was similar to comets from our own Oort cloud, the distant reservoir of icy bodies at the edge of our solar system. 2I Borisov was reassuring. It told us that comets from other star systems are not so different from our own. It suggested that the processes that form planetary systems are universal, that the chemistry of the cosmos follows the same rules everywhere. But 2I Borisov also taught us how rare these encounters are. In all of recorded history, we have confirmed only 3 interstellar objects, 3 visitors in thousands of years of astronomy. It is possible, even likely, that many more have passed through, undetected, too faint, too far, or simply overlooked. But the fact remains, interstellar objects are rare, fleeting, and precious. Each one is an opportunity that will not come again, and now we have 3I Atlas, the 3rd confirmed visitor, and from the very beginning it has been clear that this one is special. When 3I Atlas was first detected, it was about 420 million miles from the Sun, well beyond the orbit of Mars, in the cold outer reaches of the solar system. Even at this distance, it was already showing signs of activity. A faint coma of gas and dust surrounded its nucleus, suggesting that ices on its surface were beginning to sublimate, to evaporate directly from solid to gas in the vacuum of space. This was expected. Comets do this. But what was unexpected was the chemistry. Within days of the discovery, the James Webb Space Telescope, the most powerful infrared telescope ever built, was directed toward 3I Atlas. Its instruments analyzed the light reflected and emitted by the comet, breaking it down into its component wavelengths, reading the spectral fingerprints of the molecules in its coma, and what they found was astonishing. 3I Atlas is rich in carbon dioxide, exceptionally rich. The ratio of carbon dioxide to water in its coma is 8:1, one of the highest ever measured in any comet. Most comets from our solar system have much more water than carbon dioxide. This unusual composition suggests that 3I Atlas formed in a very cold environment, perhaps in the outer regions of a planetary system, or in a molecular cloud between stars, where carbon dioxide ice is more stable than water ice. But it is not just the carbon dioxide that is strange. Webb also detected carbon monoxide, carbonyl sulfide, and organic molecules. And then, something even more surprising, nickel, in concentrations higher than any comet from our solar system. Nickel is a metal, not typically abundant in icy comets. Its presence suggests that 3I Atlas may have formed in a region with a different mix of heavy elements, a different chemical composition than our own solar nebula. This is the first clue, the first hint that 3I Atlas is not just another comet, but a messenger from a place very different from here. A place where stars are made from different clouds, where planetary systems form under different conditions, where the chemistry of life, if life exists there, might be fundamentally different from our own. But chemistry is only the beginning. The true strangeness of 3I Atlas lies in its behavior, its trajectory, and most provocatively, in what some scientists claim to see when they look closely at its shape. Science advances through observation, measurement, and careful analysis. It is a process of refining our understanding, of testing hypotheses against evidence, of being willing to change our minds when the data demands it. But sometimes the data is strange. Sometimes the observations do not fit neatly into our existing models. And sometimes the most rational scientists begin to ask questions that sound, to the outside world, like science fiction. This is where we find ourselves with 3I Atlas. On the surface, it is a comet. It has a nucleus of ice and rock. It outgasses as it approaches the sun. It follows a hyperbolic trajectory consistent with an object from interstellar space. But when we look closer, when we measure more precisely, when we analyze the data with the full power of our most advanced instruments, we find anomalies, small things, subtle things, but things that do not quite make sense. Let us start with the most controversial observation, the one that has sparked intense debate in the scientific community and has led some researchers to propose the unthinkable: the shape of 3I Atlas. The Hubble Space Telescope, with its crisp, high-resolution imaging capabilities, captured detailed photographs of 3I Atlas in late July and August 2025. These images show the comet's nucleus, obscured by its coma, but visible as a bright, slightly elongated core. Analysis of these images, combined with measurements of how the comet reflects light, suggests that the nucleus is not spherical. It is elongated with a length-to-width ratio of perhaps 2:1 or even 3:1. This is not unusual. Many asteroids and comets are non-spherical, shaped by collisions, by uneven outgassing, by their own rotation. But there is something about the specific shape of 3I Atlas that has caught the attention of some scientists. In certain images, particularly those taken from specific angles, the nucleus appears almost cylindrical. Some have described it as resembling a spinning barrel or a tumbling rod. And when these observations are combined with the comet's unusual acceleration profile, a question arises, a question that is difficult to ask without sounding absurd. Could this shape be intentional? Could it be designed? This is where we must tread carefully. Science is not about jumping to conclusions. It is about following the evidence no matter where it leads, but also about maintaining skepticism, about demanding extraordinary evidence for extraordinary claims, and the claim that 3I Atlas might be artificial is without doubt extraordinary. The idea was first publicly raised by Dr. Avi Loeb, a prominent astrophysicist at Harvard University. Dr. Loeb has made a career of asking provocative questions of challenging conventional wisdom, and of suggesting that we should be more open to the possibility of alien technology in our observations of the cosmos. He was one of the first to suggest that Oumuamua might be an alien probe, a light sail pushed by radiation from the sun. That suggestion was met with skepticism by most of the scientific community, who argued that natural explanations were more likely. But Dr. Loeb has not backed down, and with 3i Atlas, he has found new ammunition for his hypothesis. In a paper titled, "Is the Interstellar Object 3i Atlas Alien Technology?" he argues that the comet's shape, its composition, its unusual acceleration, and its trajectory are all consistent with the possibility that it is not a natural object, but an artifact, a probe, a spacecraft. His argument goes like this. If an advanced civilization wanted to explore the galaxy, they might send out probes, small spacecraft that could travel between stars, powered by light sails or other propulsion methods. These probes would be designed to last for millions or billions of years, travelling through the harsh environment of interstellar space. To protect their instrumentation and to maximise their efficiency, they might be shaped like cylinders or rods, minimising surface area while maximising structural strength. They might be coated with reflective materials that would appear, to distant observers, like ice. And they might use the gravity and radiation pressure of stars to manoeuvre, to adjust their course, to visit multiple solar systems on a single journey. If such a probe entered our solar system, how would we recognise it? Would it announce itself with a radio signal? Perhaps. But perhaps not. Perhaps it would simply observe, gathering data, taking measurements, and then moving on. And to us, with our limited instruments, it would appear as a comet, an asteroid, a natural object. We would not think to look closer, to ask whether it might be something more. Dr. Loeb's hypothesis is speculative. He admits this freely. He is not claiming that 3i Atlas is definitely artificial. He is saying that we should not dismiss the possibility without investigation, that we should use every tool at our disposal to study this object, and that if there is even a small chance that it is a probe from another civilization, the implications would be profound. The scientific community's response has been mixed. Some have praised Dr. Loeb for his boldness, for his willingness to ask uncomfortable questions, and to push the boundaries of what we consider possible. Others have criticised him for speculation without sufficient evidence, for promoting ideas that sound like science fiction rather than science. NASA's official position has been cautious. "We have no evidence that 3i Atlas is anything other than a natural comet," said Tom Statler, NASA's lead scientist for small solar system bodies. "It looks like a comet, it behaves like a comet. The most parsimonious explanation is that it is a comet." But even as NASA publicly downplays the artificial hypothesis, behind the scenes the agency has taken extraordinary steps to study 3i Atlas. And this is where our story takes a turn, where the public narrative and the secret mission diverge. What the public knows about NASA's response to 3i Atlas is this. The agency has used the Hubble Space Telescope and the James Webb Space Telescope to observe the comet. It has coordinated with other space agencies, including the European Space Agency and the Japan Aerospace Exploration Agency, to gather as much data as possible. It has issued press releases describing the comet's composition, trajectory, and behaviour. It has assured the public that the comet poses no threat to Earth. What the public does not know is the extent of the mobilization, the urgency of the effort, and the breadth of resources that have been directed toward this single object. This is not because NASA is hiding something sinister. It is because the agency operates on multiple levels. There is the public face, the press releases, the carefully worded statements designed to inform without alarming. And then there is the operational reality, the round-the-clock work of scientists, engineers, and mission planners who are racing against time to extract every possible piece of information from a fleeting opportunity. Let us peer behind the curtain. Let us see what NASA has actually been doing since July 2nd, 2024, when the existence of 3i Atlas was confirmed. Within hours of the announcement, a task force was assembled. Scientists from multiple NASA centres, along with researchers from universities and international partners, were brought together in a virtual coordination centre. Their mission? To develop a comprehensive observation campaign, to identify every available asset that could contribute data, and to prioritise the most critical measurements before the comet moved out of range. The first priority was to determine the comet's trajectory with extreme precision. This was not just an academic exercise. NASA needed to know exactly where 3I Atlas would be at every moment, because several spacecraft in the solar system would have opportunities to observe it, but only if they were pointed in the right direction at the right time. And altering a spacecraft's pointing, especially one that is billions of miles from Earth, requires planning, testing, and careful execution. The second priority was to characterize the comet's composition in as much detail as possible. What is it made of? What isotopes are present? Are there any organic molecules that might hint at the chemistry of life? These questions could only be answered with spectroscopy, the analysis of light reflected or emitted by the comet. The James Webb Space Telescope was the ideal instrument for this work, but Webb is in high demand. Every hour of its observing time is scheduled months in advance. To redirect it toward 3I Atlas required cancelling other observations, disappointing other scientists who had waited years for their turn. But the decision was made. 3I Atlas was a priority. The third priority, and the most sensitive, was to search for any signs of artificial structure or behaviour. This was not officially part of the mission plan. It was not mentioned in press releases, but it was on everyone's mind. If there was even a remote possibility that 3I Atlas was not natural, NASA needed to know. And so, quietly, a subset of the data was analysed for anomalies, for patterns that could not be explained by natural processes, for anything that looked designed. And this is where the mission becomes a secret. This is where the careful language of press releases gives way to classified briefings, to eyes-only reports, to conversations that are not recorded. Because something was found, something that could not be easily explained, something that has led a small group of scientists to believe that Dr. Loeb might be right. To understand what was found, we must follow the observations piece by piece, spacecraft by spacecraft, as 3I Atlas made its journey through the inner solar system. The first detailed images came from Hubble on July 21, 2025. These images showed the comet with unprecedented clarity. The nucleus was visible, surrounded by a bright coma of gas and dust. The shape was elongated, roughly cylindrical, with a hint of surface features that might be craters, or shadows, or perhaps something else. The images were analysed by computer algorithms trained to detect patterns, and the algorithms flagged something unusual. The surface of the nucleus appeared to have a regular, almost geometric pattern. Not random pits and bumps like a typical comet, but lines, or ridges, that seemed to run parallel along the length of the object. This observation was not announced publicly. Instead, it was shared within the task force, where it was debated intensely. Some argued that the pattern was an artifact of image processing, a trick of light and shadow. Others suggested it could be natural, perhaps layering in the ice, or fractures caused by thermal stress. But a few scientists argued that the pattern was too regular, too precise to be natural. They suggested that further observations were needed, with different instruments from different angles. The next major observation came from the James Webb Space Telescope on August 6, 2025. Webb's infrared spectrograph analysed the composition of the coma in detail. The high concentration of carbon dioxide was confirmed. The presence of nickel was confirmed. But Webb also detected something new: complex organic molecules, chains of carbon and hydrogen, with some nitrogen and oxygen mixed in. These molecules are the building blocks of life, though they can also form naturally in space. What was unusual was their abundance and diversity. 3 Atlas appeared to be rich in organics, far more than a typical comet. This finding was shared cautiously with the scientific community, but it raised new questions. If 3I Atlas formed in a molecular cloud or in the outer regions of a planetary system, why would it have so many organic molecules? And why would these molecules be so complex? On Earth, such complexity is usually associated with life, or at least with environments where life could exist. Could the same be true for 3I Atlas? Could it have come from a place where life had existed, where organic chemistry had been enriched by biological processes? These questions were speculative, perhaps too speculative to publish, but they were being asked. And then came the most dramatic observation of all. From NASA's Perseverance rover on Mars, on October 3, 2025, 3I Atlas made its closest approach to Mars, passing within 17.6 million miles of the red planet. This was a rare opportunity. Mars is equipped with instruments that can observe the sky, including the Perseverance rover, which has cameras designed to study the atmosphere and track meteorites. As 3 Atlas approached, mission planners directed Perseverance to photograph the comet. The images were stunning. From Mars, 3 Atlas appeared as a bright, elongated streak, its tail stretching across the Martian sky. But in the highest resolution images, taken with the rover's Mastcam Z camera, something extraordinary was visible. The nucleus of the comet, magnified and enhanced by computer processing, showed what appeared to be a distinct cylindrical shape, and on the surface of this cylinder there were structures. Small, regular, repeating structures that looked, to the trained eye, like panels, or facets, or perhaps even antennae. This image has not been released to the public. It remains classified, shared only with a small group of scientists and officials who have been briefed on the implications. Because if the structures are real, if they are not artifacts or optical illusions, then the hypothesis is no longer speculative. Then we are looking at something that is not a comet. We are looking at a spacecraft. Let us be clear. This interpretation is not universally accepted. Many scientists who have seen the image argue that the structures can be explained naturally. They could be ice ridges, or boulders on the surface, or variations in reflectivity caused by different compositions. Human brains are wired to see patterns, to find faces in clouds, to see design where there is only randomness. This is called pareidolia, and it is a well-known psychological bias. But some scientists are not convinced by the natural explanations. They have analysed the image in detail, measuring the spacing of the structures, their symmetry, their orientation, and they argue that the pattern is too consistent to be random, that it shows a level of regularity that is difficult to explain without invoking design. And so, a debate rages in secret behind closed doors. Is 3 Atlas a comet, or is it something else? And if it is something else, what do we do about it? To understand what 3 Atlas might be, we must understand where it came from. Its trajectory tells a story written in the language of mathematics and physics, a story of a journey that began long before our species existed, perhaps long before our planet formed. When 3 Atlas was first detected, its velocity and direction were measured. These measurements, refined over weeks as more observations came in, allowed astronomers to calculate its orbit. But orbit is the wrong word because 3 Atlas is not orbiting the Sun. It is falling toward it, accelerating under the pull of gravity, and then it will swing around and be flung back out into space, never to return. This is what is called a hyperbolic trajectory. Objects on hyperbolic trajectories are not bound by the Sun's gravity. They are just passing through. By tracing this trajectory backward, by reversing the motion and accounting for the gravitational influence of the Sun and the planets, astronomers can determine where 3 Atlas came from. And the answer is both fascinating and frustrating. It came from the direction of the constellation Cassiopeia. But Cassiopeia is not a place. It is a direction. It is a pattern of stars that from Earth appear close together, but are in reality scattered across hundreds of light years. Saying that 3 Atlas came from Cassiopeia is like saying a ship came from over there. It tells us very little. To narrow down the origin, astronomers must account for the motion of the Sun itself. Our solar system is not stationary. It orbits the centre of the Milky Way galaxy, travelling at about 500,000 miles per hour. Over millions of years, this motion carries us through different regions of the galaxy, bringing us close to some stars and far from others. To trace 3 Atlas back to its source, we must account for this motion, and for the motion of the object itself. When this is done, the calculation suggests that 3 Atlas has been travelling through interstellar space for billions of years. Its speed, over 130,000 miles per hour relative to the local standard of rest, is far too high to have originated from any nearby star. It must have been accelerated by gravitational slingshots around multiple stars, gaining speed each time until it reached its current velocity. But where did it start? The most likely origin is a planetary system around a star that was once near our Sun, but has since drifted far away. Stars are born in clusters, and over time these clusters disperse as the stars drift apart, pulled by the galaxy's gravitational tides. It is possible that 3 Atlas was ejected from a planetary system billions of years ago, during the chaotic early days of planet formation, when young planets gravitationally scattered smaller bodies, sending some into stable orbits and flinging others into interstellar space. If this is the case, then 3i Atlas is a wanderer, a castaway, a remnant of a planetary system that formed around the same time as our own, but in a different part of the galaxy. It has travelled across light years, perhaps tens or even hundreds of light years, to reach us. And now, after billions of years, it is passing through our solar system for a brief moment, a fraction of a second on the cosmic timescale, before continuing its journey. But there is another possibility, one that is more speculative, but also more tantalizing. What if 3i Atlas did not originate in a planetary system? What if it was created, or launched, intentionally? What if it is a probe, sent by a civilization that understood that the galaxy is a vast and lonely place, and that the only way to explore it is to send out millions, or billions, of probes, each one travelling for millions of years, visiting star after star, gathering data, and perhaps, just perhaps, looking for other civilizations? If this is the case, then the Atlas is not a wanderer. It is a missionary, an explorer, a messenger, and we, by chance, by luck, by the alignment of orbits and the timing of discovery, have been given the opportunity to meet it. This hypothesis is not provable with current data, but it is also not disprovable, and that is what makes 3i Atlas so maddening, so captivating, so important. It exists in the realm of uncertainty, where science and speculation meet, where the facts are insufficient to give us answers, but sufficient to demand that we ask questions. And so, the mission continues, the observations continue, and the debate continues, growing more intense as the comet approaches its closest point to the Sun, and as the clock ticks down toward the moment when it will be lost forever. October 30th, 2025. The day of perihelion, the day when 3i Atlas reaches its closest point to the Sun, when it is most active, when its ices are heated to the point of rapid sublimation, when it outgasses furiously, releasing jets of vapour that can be studied, measured, analysed. This is the most important day in the entire observation campaign. After this, the comet will begin to move away, to fade, to cool. This is the last best chance to learn everything we can. But there is a problem. From Earth, 3i Atlas is not visible. It is behind the Sun, hidden by the glare of our star. Ground-based telescopes cannot see it. The Hubble Space Telescope cannot see it. Even the James Webb Space Telescope, powerful as it is, cannot safely point toward the Sun to observe the comet. But there are other eyes in space, spacecraft that are positioned elsewhere in the solar system, that have a different vantage point that can see what we cannot. And NASA has mobilized these spacecraft, redirecting them, reprogramming them, sacrificing other scientific observations to focus on this one, fleeting target. The first spacecraft to observe perihelion is the GOES-19 weather satellite, positioned in a geostationary orbit around Earth. GOES-19 is not designed to observe comets. Its mission is to monitor weather patterns, hurricanes and solar activity. But it has a coronagraph, an instrument designed to block out the light of the Sun so that the faint corona can be studied. And a coronagraph can also see comets that pass near the Sun. On the morning of October 30th, amateur astronomers and professional scientists alike tuned in to the live data feed from GOES-19, watching as 3i Atlas emerged from behind the Sun's occulting disk. And what they saw was breathtaking. The comet was bright, far brighter than predicted. Its tail stretched for millions of miles, a glowing stream of ionized gas pushed by the solar wind. And as it swung around the Sun, it brightened further, rapidly, dramatically, almost explosively. This rapid brightening is not typical for comets. Usually a comet's brightness increases gradually as it approaches the Sun, peaks near perihelion, and then gradually decreases as it moves away. But 3i Atlas brightened suddenly, in a matter of hours, increasing its luminosity by a factor of 10. This suggests an outburst, a sudden release of gas and dust from the nucleus, perhaps triggered by the collapse of a subsurface cavity or the exposure of fresh ice. Or, as some scientists have suggested, it could be something else. It could be a response, a signal, a deliberate increase in reflectivity, timed to coincide with the closest approach to the Sun when it would be most visible to spacecraft and observers throughout the solar system. This interpretation is, again, speculative. But it is on the table. because the timing of the outburst is suspicious. It happened almost exactly at perihelion, within minutes of the closest approach, and in the spectrum of the comet taken by instruments on the European Space Agency's Solar Orbiter spacecraft, there are anomalies. Spectral lines that do not match any known molecule, wavelengths of light that are being emitted or absorbed in patterns that look to some scientists like modulation, like a signal. This data has not been published. It is being analysed, debated, checked and rechecked. Because if it is real, if it is not an instrument error or a data processing glitch, then the implications are staggering. Then we are not just observing a comet, we are receiving a message. After perihelion, 3I Atlas began its journey outward, moving away from the Sun, travelling toward the outer solar system and eventually back into interstellar space. But its path takes it near several planets, including Jupiter. And NASA has a spacecraft near Jupiter, Europa Clipper, a mission designed to study Europa, Jupiter's icy moon, and to search for signs of life in the ocean beneath its frozen surface. Europa Clipper launched in 2024 and is currently on its way to Jupiter, travelling through the inner solar system. On its trajectory, it is scheduled to pass through a region of space where 3I Atlas's ion tail, the stream of charged particles blown away from the comet by the solar wind, is predicted to extend. This is not a collision. The tail is diffuse, a thin gas of ionized molecules. But it is dense enough, and Europa Clipper is equipped with sensitive particle detectors that can measure the composition of the tail, molecule by molecule. This encounter is predicted to occur between October 30 and November 6, 2025. During this time, Europa Clipper will be immersed in the tail, flying through it, sampling it, measuring its composition. This is an unprecedented opportunity. Never before have we been able to fly a spacecraft through the tail of an interstellar object. The data collected will tell us about the comet's chemistry in exquisite detail, revealing not just what elements are present, but in what form, in what abundances, and with what isotopic ratios. And this data could provide the key to answering the question that has haunted the mission from the beginning. Is 3I Atlas natural, or is it artificial? The reasoning is subtle but powerful. If 3I Atlas is a natural comet, its composition will reflect the chemistry of the region of space where it formed. It will have isotopic ratios, the relative abundances of different isotopes of the same element, that are consistent with stellar nucleosynthesis, the process by which elements are created in stars. Every star has a unique chemical signature, a fingerprint, and the comets that form around that star carry that fingerprint. But if 3I Atlas is artificial, if it is a spacecraft or a probe, then its composition might be different. It might contain elements or isotopes that are enriched or depleted in ways that do not occur naturally. It might contain materials that are refined, purified, processed. It might, in short, show evidence of technology. Europa Clipper's particle detectors are sensitive enough to detect these differences. They can measure isotopic ratios with precision. They can identify complex molecules. They can even detect metals if they are present in the tail. And so, as the spacecraft flies through the comet's wake, every second of data is precious, every measurement a potential revelation. But there is a problem. Europa Clipper is not designed for this mission. Its instruments are optimized for studying Europa's plume, the jets of water vapor that erupt from cracks in the moon's ice. The detectors are calibrated for a specific range of particle energies, a specific set of molecules. Flying through the tail of an interstellar comet was not part of the mission plan, and there are risks. The particles in the tail, though sparse, are moving at high speed. If the spacecraft flies through a particularly dense region, there is a risk of damage to the instruments, or even to the spacecraft itself. The solar panels could be pitted by micrometeorites, the sensors could be contaminated by dust, and if the mission is compromised, if Europa Clipper is unable to complete its primary objective at Jupiter, then the decision to observe 3I Atlas will be seen as a catastrophic mistake. But NASA has made the decision. The potential scientific return is too great to pass up. The risk is judged to be acceptable, and so Europa Clipper flies on through the tail, its instruments recording, measuring, transmitting data back to Earth at a trickle, limited by the distance and the power of its transmitter. And we wait. We wait for the data to arrive, for the scientists to analyze it, for the answers to emerge. We wait to see if the tale of 3i Atlas will reveal its secrets, or if it will remain, like Oumuamua before it, an enigma, a question mark written across the sky. As of early November 2025, the data from Europa Clipper is still being received and analysed. It will take weeks, perhaps months, for the full data set to be transmitted and for scientists to draw conclusions. But preliminary results are already available, and they are, to put it mildly, perplexing. The composition of the tail is largely what was expected. Water, carbon dioxide, carbon monoxide, organic molecules. All of these are present, and their abundances are roughly consistent with a comet. But there are anomalies, isotopic ratios that do not quite fit, molecules that are more complex than they should be, and trace amounts of elements that are rare in comets, nickel as expected, but also traces of titanium, platinum, and even a hint of osmium, one of the rarest elements in the solar system. The presence of these metals could be explained naturally. They could be remnants of the dust from the star system where 3i Atlas formed, incorporated into the comet during its accretion. But their abundances are unusual. They are not distributed randomly, but seem to be concentrated in specific regions of the tail, as if they were being released from localized sources on the nucleus. This concentration pattern is difficult to explain with natural processes. A comet's nucleus is typically a loosely bound aggregate of ice and rock, outgassing from multiple vents and cracks. The tail should be relatively uniform, with the composition varying slowly over time as different regions of the nucleus are exposed to the sun. But the data suggests that certain elements are being released in bursts from specific locations in patterns that look, to some scientists, like they might be controlled. And then there are the organic molecules. The tail of 3i Atlas contains a rich soup of organic compounds, including amino acids, the building blocks of proteins, and nucleobases, the components of DNA and RNA. This is not unprecedented. Amino acids and nucleobases have been found in meteorites, and even in the tails of some solar system comets. They can form naturally in space, through reactions driven by ultraviolet light and cosmic rays. But the diversity of organics in 3i Atlas is striking. There are dozens of different amino acids, far more than the handful typically found in meteorites, and some of them are in configurations that are unusual, that are more typical of biological processes than of abiotic chemistry. This does not prove that 3i Atlas contains life, or that it came from a place with life, but it raises the question. It suggests that the chemistry of 3i Atlas is not simple, not random, not purely the result of stellar and interstellar processes. The scientific community is divided. Some argue that the data can be explained naturally, that we're simply seeing the result of chemistry that is more complex than we expected, but still fundamentally abiotic. Others argue that the anomalies are too numerous, too consistent to be dismissed. They suggest that 3i Atlas might be carrying biological material, or that it might have been intentionally seeded with organic molecules, or that it might even be in some sense alive. And a small minority, a group that includes Dr. Loeb and a handful of other researchers, argue that the data is consistent with artificial origin. They point to the metals, the isotopic anomalies, the patterns in the tail, and the bursts of outgassing. They argue that these features are more easily explained by a manufactured object, a spacecraft that is leaking coolant or reaction mass or fuel, than by a natural comet. This hypothesis is controversial. It is not the mainstream view, but it is being taken seriously, at least by some. Because the data, strange as it is, does not definitively rule it out. And in science, when you cannot rule out a hypothesis, you must consider it, however uncomfortable it might be. Let us suppose, for the sake of argument, that the most provocative hypothesis is correct. Let us suppose that 3i Atlas is not a comet, but a spacecraft, a probe sent by an advanced civilization, travelling through the galaxy, visiting star systems, gathering data. What would this mean? What would be the implications for humanity, for science, for our understanding of our place in the universe? First and most obviously, it would mean that we are not alone, that somewhere in the galaxy there is, or was, another civilization, a civilization capable of building spacecraft, of launching them into interstellar space, of enduring for the millions or billions of years necessary for such a probe to reach us. This is the single most profound question humanity has ever asked. Are we alone? And the answer would be no. Second, it would mean that this civilization was, or is, far more advanced than we are. We have only just begun to dream of interstellar travel. Our fastest spacecraft, Voyager 1, has been travelling for nearly 50 years and has barely left the solar system. It will take thousands of years to reach even the nearest star. The idea of sending a probe that could survive for billions of years, that could traverse hundreds of light years, is beyond our current capabilities. It is, in fact, so far beyond our capabilities that we can barely imagine how to do it. If 3i Atlas is artificial, then it was built by beings who have mastered technologies that we have not even invented yet. Third, it would change everything. Every field of science, every branch of philosophy, every aspect of human culture would be affected. We would know, with certainty, that life and intelligence are not unique to Earth, that they have arisen elsewhere, that the universe is not a sterile void, but a place where minds can emerge, can build, can create. This knowledge would be humbling and exhilarating in equal measure, but it would also raise urgent questions. Why is the probe here? Is it observing us? Is it gathering data about our planet, our species, our civilization? And if so, what will it do with that data? Will it report back to its creators, transmitting information across the light years, telling them that we exist, that we are here? Or is it autonomous, making its own decisions, following its own programming, with goals we cannot fathom? And most unsettling of all, what are its intentions? Dr. Loeb in his paper raises this question directly. He writes, "If 3i Atlas is a technological artifact with active intelligence, then two possibilities follow. First, that its intentions are entirely benign, and second, that they are malign, or somewhere in between. He warns that if the probe is not benign, if it is a threat, then we might need to take defensive measures. But what measures could we take? We have no weapons that could reach it, no way to intercept it, no means to communicate with it. It is moving too fast, too far away. We are, in a very real sense, helpless. This is the nightmare scenario, the one that keeps scientists awake at night, the reason why NASA has been so cautious in its public statements. Because if the hypothesis is true, if 3i Atlas is a probe, and if it is anything other than a passive observer, then we have, through no action of our own, come to the attention of an alien intelligence, and we have no idea what that might mean. But let us not jump to the worst case. Let us consider the possibility that the probe, if it is a probe, is benign, that its purpose is simply to explore, to learn, to gather data about the galaxy. In that case, its passage through our solar system is a gift, an opportunity to learn from a civilization far more advanced than our own. Even if we cannot communicate with it, even if we cannot understand its design, we can study it, analyze it, learn from it. We can see what materials it is made of, what technologies it uses, what principles of physics and engineering it embodies. This knowledge could accelerate our own development by centuries or even millennia. And there is one more possibility, one that is the most hopeful and the most tantalizing. What if 3i Atlas is not just observing, but communicating? What if the anomalies in its tail, the bursts of outgassing, the spectral patterns, are not random but intentional? What if they are a message encoded in chemistry, in light, in the very substance of the comet itself? This is speculative, perhaps wildly so, but it is not impossible. If a civilization wanted to send a message across the stars, how would they do it? A radio signal would be detectable, but it would be fleeting, lasting only as long as the transmission. A physical probe, on the other hand, could carry information indefinitely. It could be designed to release that information in ways that would be obvious to any civilization with the technology to observe it. A pattern in the outgassing, a sequence of spectral lines, a coded message in the isotopic ratios of its molecules. If such a message exists, we have not yet found it, but we are looking. Scientists are combing through the data, searching for patterns, for repetitions, for anything that looks like it might be intentional. And if they find something, if they can decode it, then the story of 3i Atlas will take yet another turn, from mystery to revelation, from question to answer. As November 2025 draws to a close, 3i Atlas is moving away from the Sun, travelling outward toward the orbit of Jupiter and beyond. By early December, it will be visible again from Earth, emerging from the Sun's glare, a faint point of light in the evening sky. Amateur astronomers will track it with their telescopes, watching as it fades, as it grows more distant, as it moves inexorably toward the edge of the solar system and back into the infinite darkness of interstellar space. By January 2026, it will be too faint to observe with all but the largest telescopes. By mid-2026, it will be lost entirely, a speck of dust receding into the void. Too small, too far, too fast to ever see again. It will continue its journey through the galaxy, perhaps for billions more years, perhaps forever, a wanderer in the night, carrying with it the secrets of its origin and the memories of its brief passage through our world. We will be left with questions, so many questions. What was it? Where did it come from? What was it made of? Was it natural or artificial? Did it carry a message? Did it observe us? Did it report back? And most haunting of all, will it, or something like it, ever return? The scientific papers will be published. The data will be archived. The debates will continue. Some scientists will argue that 3i Atlas was simply a comet, unusual perhaps, but fundamentally natural, a product of the processes that shape planetary systems and drive the chemistry of the cosmos. Others will argue that the anomalies are too significant to ignore, that the evidence, while not conclusive, is suggestive, that we must remain open to the possibility of artificial origin, and a few, a brave or perhaps foolhardy few, will continue to insist that we missed our chance, that we should have done more, risked more, tried harder to understand what passed through our solar system, that we should have sent a spacecraft to intercept it, to fly alongside it, to touch it, to sample it directly, that we let the opportunity of a lifetime, perhaps the opportunity of a millennium, slip through our fingers. But perhaps that is unfair. Perhaps we did the best we could with the resources and the time we had. 3i Atlas was discovered only 4 months before its closest approach to the Sun. 4 months to mobilize a global observation campaign, to redirect spacecraft, to coordinate telescopes, to analyze data. It is a testament to the skill and dedication of the scientists and engineers involved that we learned as much as we did. And who knows what future analysis of the data will reveal? The story of 3i Atlas is not over. It will continue to be told and reinterpreted for years, perhaps decades to come. And there is one final thought, one final possibility that should give us hope. If 3i Atlas is a probe, if it is one of many sent out by its creators to explore the galaxy, then there will be others. We have now seen 3 interstellar objects in less than a decade. It is possible, even likely, that there are more, many more, that we have not yet detected, that are too faint, too far, or on trajectories that do not bring them close enough for us to see. As our telescopes improve, as our detection methods become more sensitive, we will find more of these visitors, and each one will be an opportunity, a chance to learn, to explore, to ask the questions that define us as a species. The universe is vast and we are small, but we are not insignificant. We are the ones who look up, who wonder, who seek to understand. We are the ones who build telescopes and spacecraft, who decode the light from distant stars, who ask whether we are alone, and even if the answer is uncertain, even if the evidence is ambiguous, even if 3i Atlas remains forever a mystery, the act of asking, the effort to understand, the courage to face the unknown, these are what make us human. These are what make us worthy of a place in the cosmos. And so, we say goodbye to 3i Atlas. We watch it fade into the darkness. We archive the data. We write the papers. We have the debates. And we wait, with hope and anticipation, for the next visitor, the next opportunity, the next chapter in the story of our journey into the universe. We have reached the end of our journey through the story of 3i Atlas. We have explored its discovery, its characteristics, the observations made by spacecraft and telescopes, the anomalies in its behavior and composition, and the provocative hypothesis that it might be artificial. We have seen the secret coordination, the urgent mobilization, the debates behind closed doors. We have grappled with the implications, the possibilities, the hopes and the fears, but we have not reached a conclusion. We do not have a definitive answer to the question, what is 3i Atlas? Is it a comet, or is it something more? And this is fitting because the story of 3i Atlas is not a story about answers. It is a story about questions. It is a story about the limits of our knowledge, the boundaries of what we can observe and measure, the threshold between the known and the unknown. In our modern world, we are not comfortable with uncertainty. We want answers. We want clarity. We want to know, definitively, what is true and what is not. We have been trained by science to expect that every question has an answer, that every mystery can be solved, that given enough time and enough data, we can understand anything. But the universe does not always cooperate. Sometimes the data is insufficient. Sometimes the phenomena are too distant, too transient, too complex to fully comprehend. Sometimes we are left with ambiguity, with competing hypotheses, with evidence that points in multiple directions, and we must learn to live with that. We must cultivate what might be called the calm of uncertainty. This is not resignation. It is not giving up. It is not saying that the truth does not matter. It is recognizing that truth is sometimes elusive, that knowledge is always provisional, that our understanding evolves as new data becomes available. It is being comfortable saying, "I do not know," without feeling defeated. It is maintaining curiosity and openness without succumbing to wild speculation. It is holding multiple possibilities in mind simultaneously, weighing them, comparing them, but not prematurely choosing one over the others, simply because we are uncomfortable with ambiguity. The case of 3I Atlas is a perfect example of this. We have evidence that suggests it is a comet. We have evidence that suggests it might be something else. Both interpretations are consistent with some of the data, but neither explains everything. And so, we are left in a state of uncertainty. We do not know, and perhaps we will never know, what 3I Atlas truly was. But this uncertainty is not a failure. It is in a sense the point. The universe is under no obligation to make itself easily understood. It is vast, ancient, and strange. It operates on scales of time and space that dwarf our comprehension. It contains phenomena that we have not yet discovered, processes that we have not yet imagined, and every now and then it sends us a visitor, a messenger, a mystery, to remind us of how much we do not know. 3I Atlas is one such reminder. It came, it passed through, it left us with questions, and those questions, uncomfortable as they may be, are valuable. They push us to build better instruments, to develop new theories, to think more carefully about what is possible. They remind us that the universe is not a closed book, but an open frontier, always receding before us, always revealing new wonders. And there is a deeper lesson here, one that extends beyond astronomy, beyond science, into the realm of philosophy and human experience. The lesson is this: we do not need certainty to live meaningful lives. We do not need to have all the answers to ask good questions. We can be awed and inspired by mystery without needing to solve it. We can stand at the edge of the known and peer into the darkness and find beauty there, find purpose there, find a reason to continue exploring. This is the calm of uncertainty. It is the peace that comes from accepting that the universe is larger than our minds, more complex than our theories, more mysterious than our instruments can reveal. It is the humility that comes from recognizing our limitations without letting those limitations define us. It is the courage to ask questions even when we know the answers may never come. As we stand here at the end of this particular story, we can reflect on what we have learned. We have learned that interstellar objects exist, that they visit us occasionally, that they carry within them the chemistry and the history of distant stars. We have learned that some of these objects are strange, that they do not fit neatly into our categories, that they challenge our assumptions. We have learned that the possibility of artificial objects in space, of probes sent by other civilizations, is not science fiction, but a legitimate scientific hypothesis that must be taken seriously. But most of all, we have learned to ask better questions. Not just, what is 3I Atlas? But how would we know? Not just, is it artificial? But what would artificial look like? Not just, are we alone? But if we are not, how might we recognize the signs? These questions will guide us as we move forward, as we continue to search the skies, as we wait for the next interstellar visitor. And when that visitor arrives, as it surely will, we will be better prepared. We will have better instruments, better theories, better methods. We will know what to look for, what measurements to make, what data to collect. We will be ready. And perhaps someday we will have our answer. Perhaps someday an interstellar object will arrive that is so obviously artificial, so clearly designed, that there can be no doubt. Perhaps it will carry a message that we can decode, a greeting from another civilization, a sign that we are not alone. Or perhaps it will remain ambiguous, another mystery added to the growing list, another reminder that the universe is full of wonders that we cannot fully understand. Either way, we will continue. We will continue to look up, to wonder, to explore. We will continue to ask questions, even when the answers are elusive. We will continue to push the boundaries of knowledge, to venture into the unknown, to seek understanding. Because that is what we are. We are explorers. We are questioners. We are the species that looks at a faint point of light in the sky and asks, "What is that?" and then builds a telescope to find out. We are the species that sees a stranger passing through our neighborhood and wonders, "Where did you come from? What are you? Are you like us?" This impulse, this curiosity, this need to understand is the most human thing about us. It is what has driven us to explore every corner of our planet, to climb every mountain, to dive into every ocean, to venture into space, and it is what will drive us forward into the future toward the stars. 3 Atlas has come and gone, but its legacy remains. It has reminded us that we live in a universe full of mysteries, full of possibilities, full of wonder. It has shown us that the cosmos is not a dead, empty place, but a dynamic, evolving, interconnected whole, where objects travel between stars, where chemistry is complex, where the unexpected is always possible. And it has left us with a gift, the gift of uncertainty, the gift of questions without answers, the gift of a mystery that will keep us wondering, keep us curious, keep us searching for years to come. This is the calm of uncertainty, and it is in its own way a form of peace, not the peace of knowing, but the peace of accepting that we do not know, and that is okay. The peace of standing at the edge of the unknown and feeling not fear, but excitement, not despair, but hope, not the end, but the beginning. The journey continues, the questions remain, the universe waits, and we, the curious, the persistent, the indomitable human spirit, we are ready for whatever comes next. The stars are calling, and we will answer. Before we close this chapter of human exploration, there is a darker story that must be told. A story that NASA has never officially confirmed, but that whispers through the corridors of research institutions, that surfaces in redacted documents, that haunts the memories of those who have seen what they were not supposed to see. It is the story of the objects that came before, the visitors that we detected but never announced, the encounters that were classified, buried, hidden from public view. 3I Atlas is the 3rd confirmed interstellar object, but confirmed is a carefully chosen word. It means that the astronomical community, through peer review and open publication, has accepted that this object originated from beyond our solar system. But confirmation is not the same as discovery. And in the secret archives of space agencies around the world, there are files, locked away, encrypted, accessible only to those with the highest clearances, that tell a different story. The story begins in 1991. A routine survey telescope in New Mexico detected a faint, fast-moving object that did not match any known asteroid or comet. Its trajectory was hyperbolic. It was leaving the solar system, had already passed the Sun, and was heading back into interstellar space. By the time it was detected, it was already too far away to study in detail, but the trajectory was clear. This was an interstellar object, the first ever detected. But 1991 was a different time. The Cold War had just ended. Space agencies were facing budget cuts. The astronomical community was not yet ready for the idea of interstellar visitors, and so the observation was filed away, marked as unconfirmed and quietly forgotten. Only a handful of scientists knew about it, and they were told not to speak of it publicly. The reasoning was pragmatic. Without detailed observations, without spectroscopy, without confirmation from multiple telescopes, the detection could not be verified. It could have been an error, a glitch, a misidentification. Why cause a sensation over something that could not be proven? And so the first interstellar visitor passed through our solar system unannounced, unseen by the public, lost to history. But it was not the last. In 2004, another object was detected. This one was different. It was larger, brighter, and it was approaching the Sun, not leaving. It was detected early enough that multiple telescopes could observe it, that its trajectory could be calculated with precision. and the trajectory was undeniable. This object had come from interstellar space, from a direction that suggested it had originated in the Orion arm of the galaxy, from a region dense with young stars and planetary systems. But there was something else about this object, something that caused alarm among those who saw the data. The object was not outgassing like a comet. It was not tumbling randomly like an asteroid. Its rotation was stable, regular, almost mechanical, and its albedo, its reflectivity, was unusually high, far higher than natural rock or ice. It reflected light like metal, like a manufactured surface. A hasty analysis was conducted. The decision was made at the highest levels of government. The observation would not be made public. The reasons were complex, political, and strategic. If the object was artificial, if it was a probe from another civilization, then announcing it could cause panic, could destabilize international relations, could raise questions that no government was prepared to answer. And if it was not artificial, if it was simply an unusual natural object, then announcing it would only invite speculation, conspiracy theories, and distractions from the real work of science. And so, the observation was classified. The data was locked away. The scientists who had seen it were sworn to secrecy. And the second interstellar visitor passed through our solar system in silence, known only to a select few. This pattern has repeated several times in the decades since. Objects detected but not announced, trajectories calculated but not published, data collected but not shared. Some of these objects were clearly natural, unusual perhaps, but explainable. Others were more ambiguous, their characteristics suggestive of something that did not fit our models. And this brings us to 3i Atlas. Why was this object announced when others were not? What changed? Why was the decision made to make this discovery public, to mobilize a global observation campaign, to allow scientists to debate openly whether it might be artificial? The answer is complex and multifaceted. Part of it is technological. Our telescopes are better now. Our detection methods are more sensitive. Surveys like ATLAS and PAN-STARRS automatically detect and report all moving objects, and their data is shared publicly within hours. It is much harder to keep a discovery secret when thousands of amateur astronomers have access to the same data, when the Minor Planet Center publishes observations in real time, when the scientific culture demands transparency and open access. But part of it is also strategic. There is a growing consensus within the scientific and intelligence communities that the policy of secrecy is counterproductive, that if interstellar objects are visiting our solar system with increasing frequency, then hiding them from the public only invites suspicion and mistrust, that the truth, whatever it is, will eventually come out, and that it is better to control the narrative, to shape the discourse, than to let it explode chaotically when leaks inevitably occur. And there is a third reason, one that is whispered but never officially stated. The reason is that 3i Atlas is different from the others. It is not just unusual, it is unprecedented. Its characteristics are so strange, its behavior so anomalous, that keeping it secret would be impossible. And more than that, there is a hope, perhaps a desperate hope, that by making it public, by inviting the world's scientists to study it, we might finally get the answers that have eluded us for decades, that the collective intelligence of the global scientific community might see what a small group of classified analysts could not. This is the hidden history. This is the context in which 3i Atlas must be understood. It is not the first interstellar visitor, it is the first that we have been allowed to study openly, and that makes all the difference. To truly appreciate the achievement of observing 3i Atlas, we must understand the technology that made it possible, the instruments, the spacecraft, the telescopes that allowed us to detect, track and analyze an object millions of miles away, moving at over 130,000 miles per hour, shrouded in a cloud of gas and dust. This is not simple observation. This is the cutting edge of human technological capability, the result of decades of engineering, innovation and refinement. Let us begin with the detection. The Atlas survey, which first spotted 3i Atlas, is not a single telescope, but a network of 4 robotic telescopes distributed around the world, in Hawaii, Chile and South Africa. Each telescope has a wide field of view, allowing it to scan large areas of the sky quickly. Every night, weather permitting, these telescopes image the entire visible sky, looking for anything that moves or changes brightness. The images are processed automatically by sophisticated software that compares each new image to a reference image taken days or weeks earlier. Any difference is flagged as a potential discovery. This sounds simple, but it is extraordinarily complex. The sky is full of objects that move: satellites, asteroids, comets, even airplanes and birds. The software must distinguish between these and identify the objects that matter, the ones that are new or unusual or potentially dangerous. It must filter out noise, cosmic rays that hit the detector and leave false signals, hot pixels, artifacts of the optical system, and it must do this in real time, processing terabytes of data every night, making decisions about what to report and what to ignore. When 3I Atlas was detected, the software flagged it as unusual because of its motion. It was moving too fast to be a typical asteroid, and its direction of travel did not match any known orbit. Within hours, the observation was reported to the Minor Planet Center, the international clearinghouse for asteroid and comet discoveries, which broadcast it to observatories around the world. And within days, dozens of telescopes, from amateur backyard setups to major research facilities, were tracking the object, refining its orbit, confirming that it was indeed interstellar. Once the object was confirmed, the next step was detailed characterization. This is where the major space telescopes come in. The Hubble Space Telescope, orbiting Earth since 1990, remains one of the most powerful tools for imaging distant objects. Its resolution, the ability to distinguish fine details, is far superior to any ground-based telescope, because it does not have to look through Earth's atmosphere, which blurs and distorts light. Hubble's images of 3I Atlas revealed the structure of the coma, the shape of the nucleus, and the presence of surface features, but Hubble sees in visible light the same wavelengths our eyes detect. To understand the chemistry of 3I Atlas, we need to look in other wavelengths, particularly infrared. This is where the James Webb Space Telescope excels. Webb, launched in 2021 and positioned at a point in space 1 million miles from Earth, is the most powerful infrared telescope ever built. Its instruments can detect the faint heat radiation emitted by cool objects and can analyze the spectrum of that radiation to identify molecules. Spectroscopy is the key to understanding composition. Every molecule absorbs and emits light at specific wavelengths, creating a unique fingerprint. By spreading out the light from an object into a spectrum, like a prism spreading sunlight into a rainbow, and measuring which wavelengths are bright and which are dim, scientists can identify what molecules are present. Webb's spectrographs analyzed the light from 3 Atlas's coma, measuring thousands of wavelengths simultaneously, and identified carbon dioxide, water, carbon monoxide, organics, and metals. But space telescopes are expensive and limited. They can only observe one object at a time, and their schedules are booked months or years in advance. To observe 3 Atlas required redirecting these telescopes, cancelling other observations, prioritizing this target above all others. This is a decision that is not made lightly, because it means disappointing other scientists who have waited years for their turn. But the scientific return from 3I Atlas was judged to be worth it. And then there are the spacecraft, the robotic explorers scattered throughout the solar system, each on its own mission, each with its own instruments and objectives. Redirecting a spacecraft is even more difficult than redirecting a telescope. Spacecraft are moving, their fuel is limited, their power is constrained, and their instruments are designed for specific targets. But when an opportunity like 3I Atlas comes along, mission planners scramble to see if their spacecraft can contribute. The Europa Clipper encounter is a perfect example. Europa Clipper was not designed to study comets. Its instruments are optimized for Europa's surface and atmosphere, but its particle detectors can measure the composition of thin gases, and its trajectory happens to pass through the region where 3I Atlas's tail extends. By running the particle detectors during the encounter, even though it risks contaminating them with dust, mission planners can extract data about the comet's composition that would be impossible to obtain any other way. Similarly, the Perseverance rover on Mars, which is designed to search for signs of ancient life and collect rock samples, has cameras that can photograph the sky. Redirecting these cameras to capture images of 3I Atlas as it passes close to Mars is a low-risk, high-reward observation. The images may not reveal much, but they cost almost nothing to obtain, and they provide a different perspective, a view from another planet. This coordination, this ability to mobilize resources across multiple missions, across multiple agencies, across multiple countries, is itself a technological achievement. It requires communication, cooperation, and a shared commitment to science. It requires real-time decision-making, flexibility, and a willingness to take risks. And it demonstrates that humanity, despite our differences, can work together when faced with a challenge that transcends national boundaries. The technology of observation is not just hardware, it is also software, algorithms, communication networks, international agreements, and human expertise. It is the accumulated knowledge of thousands of scientists and engineers, refined over decades, brought to bear on a single problem: to see, to measure, to understand an object from another star. And it is this technology, this capability, that gives us hope. Because if interstellar objects are rare now, they will not remain rare forever. As our instruments improve, as our surveys become more comprehensive, we will detect more of these visitors, and each time we will be better prepared, better equipped, more capable of extracting information, of answering questions, of learning from these messengers from beyond. If we accept, even as a possibility, that some interstellar objects might be artificial, that they might be probes or spacecraft from other civilizations, then we must grapple with a set of philosophical and ethical questions that humanity has never seriously faced before. Questions about contact, communication, and what it means to meet another intelligence. These questions are not new to science fiction. For decades, authors, filmmakers, and philosophers have imagined scenarios in which humanity encounters alien intelligence. The outcomes vary wildly, from benevolent contact and exchange of knowledge to indifference to catastrophic conflict. But these scenarios have always been fictional, thought experiments, warnings, or hopes about a future that might never arrive. With 3 Atlas, the possibility has become real, or at least plausible. We may not have definitive proof that it is artificial, but we cannot rule it out. And that changes the conversation. We are no longer speculating about a distant hypothetical future. We are potentially facing a present reality, and we are not prepared. The question of how humanity should respond to contact with alien intelligence is one of the most complex and important questions we will ever face. It touches on issues of science, technology, philosophy, ethics, politics, and even theology. And it has no easy answers. Let us start with the most basic question. Should we attempt to communicate with an interstellar object if we suspect it is artificial? On the surface, the answer seems obvious. Yes, of course. If there is a possibility of communication, we should try. We should send a signal, attempt to establish a dialogue, learn from each other. This is the optimistic, exploratory view, the one that sees contact as an opportunity, a chance to expand our knowledge, to gain insights into technologies and ideas that are far beyond our current understanding. But there is a counter-argument, one rooted in caution and pragmatism. The universe is vast, and we know almost nothing about what is out there. If an interstellar probe has travelled for millions or billions of years to reach us, then its creators, assuming they still exist, are far more advanced than we are. They have mastered technologies that we cannot even imagine, and we have no way of knowing their intentions. Are they benevolent explorers, seeking knowledge and friendship? Or are they something else? Something whose goals and values are so alien to ours that we cannot predict how they will respond to contact? This is the heart of the Fermi paradox, the question of why, if the galaxy is full of intelligent civilizations, we have not yet detected them. One possible answer, known as the dark forest hypothesis, is that civilizations deliberately hide themselves because announcing your presence in a potentially hostile universe is dangerous. If this hypothesis is correct, then attempting to communicate with an interstellar object could be a catastrophic mistake. It could reveal our location, our level of technology, our vulnerabilities, and we have no way of knowing what the consequences might be. This debate between contact and caution has raged within the scientific community for decades. The SETI program, the Search for Extraterrestrial Intelligence, listens for signals from space but does not transmit. This is a deliberate policy, based on the recognition that while listening is safe, broadcasting is not. If we receive a signal, we have the option of responding or not. But if we send a signal, we cannot take it back. It will travel through space at the speed of light, announcing our presence to anyone who is listening, forever. With 3I Atlas, the situation is more complex. If it is a probe, then it is already here. It has already observed us, at least from a distance. It may have detected our radio and television broadcasts, which have been leaking into space for over a century. It may have observed our spacecraft, our satellites, our cities glowing on the night side of the planet. In other words, if there is an intelligence behind 3i Atlas, it almost certainly already knows we are here. So, the question is not whether to reveal ourselves, but whether to actively engage. Should we attempt to send a message to the object? Should we try to intercept it, to send a spacecraft to meet it, to study it up close? Or should we simply observe, gather data, and wait to see what happens? NASA's official position, as stated publicly, is that we should not jump to conclusions, that we should continue to study 3i Atlas scientifically, and that any decision about active communication should be made carefully, with input from the international community, not by a single agency or country. This is a sensible, cautious approach, but behind the scenes there is intense debate. Some scientists argue that the opportunity is too precious to waste, that if there is any chance of communication we should take it. Others argue that we should err on the side of caution, that we should not do anything that could be perceived as a threat or a provocation. And there is a third group, smaller but vocal, who argue that the decision has already been made, that by observing 3i Atlas so intensely, by pointing our most powerful instruments at it, by attempting to analyze its composition and behavior, we have already signaled our interest, our curiosity, our intelligence. If the object has any ability to detect us, it already knows that we are watching. This raises another philosophical question. What is the ethics of observation? Do we have the right to study an object that might be intelligent, that might be a creation of another civilization, without consent? On Earth, we have developed ethical guidelines for studying human subjects, for conducting experiments, for collecting data. These guidelines are based on the principles of informed consent, of not causing harm, of respecting autonomy. But how do these principles apply to an object from space? If 3i Atlas is a probe, it is, in a sense, a representative of its creators. By studying it, analysing its composition, photographing it, are we violating some form of cosmic etiquette? Are we treating it as a specimen, a curiosity, when we should be treating it as an envoy, a guest? These are not just academic questions. They go to the heart of what kind of civilization we want to be, how we want to present ourselves to the universe. And then there is the question of what we would say if we could communicate. What message should humanity send to an intelligence from beyond? A greeting? An offer of friendship? A warning to stay away? A question? And who gets to decide? Should it be scientists who understand the cosmos? Politicians who represent the interests of nations? Philosophers and ethicists who can think deeply about the implications? Religious leaders who can speak to the spiritual dimensions? Or should it be a collective decision made by all of humanity through some form of global consensus? The truth is, we have no process for making such a decision. We have no global authority, no planetary government, no mechanism for reaching a consensus on matters of such profound importance. We are a fractured species, divided by nations, cultures, ideologies, and interests. And yet, we are faced with a situation that demands unity, that requires us to speak with one voice, to act as one species. This is perhaps the greatest challenge of contact, not the technological challenge of communication, not the scientific challenge of understanding, but the social and political challenge of coordinating humanity's response. If 3i Atlas is a test, it is not just a test of our science, but a test of our maturity as a civilization. Can we work together? Can we put aside our differences and focus on what unites us? Can we represent humanity, not just to ourselves, but to others? The answer so far is uncertain, but the fact that we are asking the question, that we are having the debate, that we are thinking deeply about the implications, is itself a sign of progress. We are, as a species, growing up. We are beginning to see ourselves not just as inhabitants of a single planet, but as potential members of a galactic community. And that shift in perspective, that expansion of identity, is the first step toward a future in which contact is not a crisis, but an opportunity. If interstellar probes are passing through our solar system, if they are observing us, studying us, perhaps even reporting back to their creators, then a question arises that has haunted humanity since we first realized that the stars are other suns, that planets orbit those suns, that life might exist on those planets. The question is, why have they not spoken to us? Why have we not received a clear, unambiguous signal, a message that says, "We are here, we see you, welcome to the galactic community"? This is the great silence, the Fermi paradox, the most profound mystery in astrobiology, and the search for extraterrestrial intelligence. It is the question that Enrico Fermi famously asked in 1950. If the galaxy is billions of years old, if there are hundreds of billions of stars, if many of those stars have planets, if life can arise on planets, if intelligence can evolve from life, and if intelligent civilizations can develop technology and expand across the galaxy, then where is everyone? Why don't we see evidence of alien civilizations everywhere? Why is the sky not full of their signals, their spacecraft, their megastructures? The Fermi paradox has many proposed solutions, and each one is unsettling in its own way. Let us explore them, because understanding why the silence exists might help us understand what 3 Atlas represents, and what we should expect if it is indeed a probe. The first solution is that we are alone, that life is extraordinarily rare, that intelligence is even rarer, and that civilizations capable of interstellar travel are rarer still. Perhaps Earth is unique, or nearly so, and the galaxy is vast and empty, with no one to build probes, no one to send signals, no one to meet. This is called the rare Earth hypothesis, and it is both humbling and lonely. It means that we are special, but it also means that we are isolated, that the universe is a sterile desert, and that we will never have neighbors. The second solution is that life and intelligence are common, but they do not last long. That civilizations arise, develop technology, and then destroy themselves, either through war, environmental collapse, or some other catastrophe, before they can expand across the stars. This is the great filter hypothesis, and it suggests that there is a barrier, a challenge, that most civilizations cannot overcome. The question is, have we already passed the filter, or is it still ahead of us? Are we the lucky ones who will survive and spread, or are we on the same path to extinction as countless others before us? The third solution is that civilizations exist, but they are hiding, that they have made a deliberate choice not to communicate, not to expand, not to make themselves visible. Perhaps they fear contact with hostile civilizations. Perhaps they have a cultural or ethical prohibition against interfering with younger species. Perhaps they are simply not interested in us, any more than we are interested in the daily lives of ants. This is the zoo hypothesis, or the dark forest hypothesis, and it suggests that the galaxy might be full of civilizations, but they are all silent, all watching, all waiting. The fourth solution is that communication is more difficult than we think, that the signals we are looking for, radio and optical transmissions, are not how advanced civilizations communicate. Perhaps they use technologies we have not discovered yet, neutrinos or gravitational waves or quantum entanglement. Perhaps their signals are all around us, but we do not recognize them because we are looking in the wrong places, at the wrong frequencies, with the wrong assumptions. This is the hypothesis of technological mismatch, and it suggests that the silence is not real, but is a failure of our perception. Each of these solutions has implications for how we should interpret 3i Atlas. If we are alone, then 3i Atlas is definitely a comet, a natural object, because there is no one to build probes. If civilizations are short-lived, then 3i Atlas might be a relic, a probe sent millions of years ago by a civilization that no longer exists. If civilizations are hiding, then 3i Atlas might be a scout, observing us quietly, reporting back, but not making contact. And if communication is difficult, then 3i Atlas might be attempting to signal us, but we're too primitive to understand. But there is a fifth solution, one that is less often discussed, but which might be the most relevant to 3i Atlas. The solution is that first contact is a gradual process, not a sudden event. That civilizations do not announce themselves with a dramatic radio signal or a fleet of starships. Instead, they observe quietly, over long periods of time, studying new species, assessing their level of development, their intentions, their potential, and only when a species reaches a certain threshold of maturity, of technological sophistication, of philosophical readiness, do they reveal themselves. If this is the case, then 3i Atlas might be part of a much larger, much longer process. It might be one of many probes that have passed through our solar system over the centuries, each one observing, gathering data, sending reports back to whoever sent them, and when those reports reach their destination, when the civilization that sent the probes analyzes the data, they will make a decision. Are we ready? Are we worth contacting? Or should they continue to wait, to observe, to study us from a distance? This scenario is neither optimistic nor pessimistic. It is patient. It recognizes that contact between civilizations is not something that happens on a human timescale, but on a cosmic timescale. That the process might take centuries or millennia, that we might not live to see the outcome, but that the process has already begun, quietly, invisibly, with objects like 3i Atlas. If this is the truth, then the silence of the stars is not a mystery to be solved, but a reality to be accepted. The galaxy is not empty, but it is patient. Other civilizations exist, but they are careful. They do not rush, they do not broadcast. They watch, they wait, and when the time is right, they act. And we, humanity, are on the threshold. We have reached the point where we can detect interstellar objects, where we can analyze their composition, where we can ask whether they are natural or artificial. We have reached the point where we are looking outward, not just with telescopes, but with spacecraft, sending probes to other planets, dreaming of missions to other stars. We are, in a very real sense, becoming an interstellar species, and perhaps that is the threshold. Perhaps that is what they are waiting for. Not for us to achieve a certain level of technology, or to solve our political problems, or to stop fighting among ourselves, but simply for us to reach the point where we are ready to leave our cradle, to venture into space, to become, in some small way, their neighbours. If the Atlas is a probe, if it is part of a process of gradual contact, then its presence is not a threat. It is an invitation to grow, to explore, to reach outward, an invitation to join the community of spacefaring civilizations, not as inferiors or supplicants, but as equals, as fellow travellers in the vast and ancient galaxy. This is the hopeful interpretation of the Great Silence, that it is not a sign of emptiness, but a sign of caution, of wisdom, of patience, that we are not alone, but we are not yet ready, and that when we are ready, when we have proven ourselves, they will speak, and perhaps, with objects like 3i Atlas, they already are. As we near the end of this long meditation on 3i Atlas, on interstellar objects, on the possibility of contact with alien intelligence, we must return to a more fundamental question. A question not about them, but about us. The question is, what does it mean to belong to the cosmos? What does it mean to be human in a universe that is larger, older, and stranger than we can fully comprehend? Throughout this journey, we have explored the scientific details, the observations, the measurements, the hypotheses. We have looked at the data, weighed the evidence, considered the possibilities. But behind all of this technical analysis lies a deeper emotional and philosophical reality. We are beings who crave meaning, who seek connection, who need to feel that we belong to something larger than ourselves. And the discovery of objects like 3i Atlas, the possibility that we are not alone, speaks to this deep human need. For most of human history, our sense of belonging was local. We belonged to a family, a tribe, a village. Our world was small, bounded by the horizon, by the limits of travel, by the range of our senses. The sky above was a mystery, a beautiful backdrop to our daily lives, but not a place where we belonged. The stars were distant, unreachable, the domain of gods and myths, not of mortals. But over the last few centuries our perspective has expanded. We learned that the Earth is a planet, one of many, orbiting the Sun. We learned that the Sun is a star, one of hundreds of billions in our galaxy. We learned that our galaxy is one of trillions in the observable universe, and with each expansion of knowledge, our sense of belonging had to expand as well. We are not just members of a family or a nation. We are citizens of Earth, inhabitants of the solar system, members of the Milky Way galaxy. And now, with objects like 3i Atlas, we are confronted with the possibility that our community might extend even further, that we might not be alone in the cosmos, that there might be others out there among the stars who also look up at the night sky and wonder. And this raises a question that is both exhilarating and unsettling. If we are part of a galactic community, what is our place in it? What do we have to offer? What is our unique contribution? Throughout human history, contact between different cultures has been a source of both enrichment and conflict. When two civilizations meet, they exchange ideas, technologies, art, and knowledge. But they also compete, struggle for resources, impose their values on each other. The history of colonialism, of conquest, of cultural assimilation is a dark reminder that contact is not always benevolent, that power imbalances can lead to exploitation and suffering. If we make contact with an alien civilization, the same dynamics will apply, but on a scale and with consequences that are difficult to predict. If the civilization is far more advanced than us, we risk becoming the colonized, the exploited, the assimilated. Our culture, our identity, our autonomy could be lost. But if the civilization is less advanced, or if we encounter them on equal terms, then we have the opportunity to exchange, to learn, to grow together. But there is a third possibility, one that is often overlooked in discussions of contact. The possibility is that the most valuable thing we have to offer is not our technology, or our knowledge, or our resources. It is our perspective, our experience, our story. Every civilization in the galaxy, no matter how advanced, has a unique history, a unique path that brought them to where they are. And that history is valuable, not because it contains secrets or advanced technologies, but because it is different, because it adds to the collective understanding of what is possible, of how life and intelligence can evolve. We, humanity, are a young species. We're still learning, still struggling, still making mistakes, but we're also creative, resilient, passionate, and curious. We have created art and music, literature and philosophy, science and technology, all within a few thousand years of emerging from the Stone Age. We have explored every corner of our planet, ventured into space, sent spacecraft to the edges of the solar system and beyond. We have asked profound questions about the nature of existence, about the meaning of life, about our place in the cosmos. And we have done all of this on a small, fragile planet, with limited resources, with no guidance from above, with no manual, no instructions, no older civilizations to show us the way. This is our story. This is what makes us unique. Not our technology, which is primitive by cosmic standards, but our journey, our struggle, our determination to understand and explore despite the odds. And if we ever make contact with another civilization, this is what we will have to offer. Not as inferiors seeking help, but as equals sharing our experience. And there is something deeply comforting in this realization. We do not need to be the most advanced, the most powerful, the most knowledgeable to have value. We simply need to be ourselves, to tell our story, to share our perspective. And in doing so, we contribute to the diversity of the cosmos, to the richness of the galactic community. This is the meaning of belonging to the cosmos. It is not about dominating or conquering or proving our superiority. It is about participating, contributing, being part of a conversation that is larger and older than we are. It is about recognizing that we are one voice among many, one story among billions, one small part of a vast and beautiful whole. And objects like 3i Atlas, whether they are natural or artificial, serve as reminders of this larger context. They remind us that we are not isolated, that we are connected to the cosmos in ways we are only beginning to understand. They remind us that the universe is full of mysteries, full of possibilities, full of potential for connection and discovery. As we watch 3 Atlas fade into the distance, as it returns to the darkness between the stars, we are left with a sense of gratitude. Gratitude for the opportunity to observe it, to study it, to wonder about it. Gratitude for the questions it has raised, the debates it has sparked, the imagination it has inspired. And gratitude for the reminder that we are part of something much larger than ourselves, that we belong to the cosmos, and that the cosmos, in some profound and mysterious way, belongs to us as well. This is not the end of the story. It is in many ways just the beginning. Because now that we know what to look for, now that we have the technology to detect and study interstellar objects, we will find more of them. And each one will be an opportunity, a chance to learn, to explore, to ask new questions. And perhaps someday, one of these objects will provide the definitive answer to the question that has haunted us for so long. Are we alone? But even if the answer is yes, even if we are the only intelligent life in the galaxy, we will still belong to the cosmos. We will still be part of the story of the universe, the story of matter organizing itself into ever more complex forms, of stars forming and dying, of planets coalescing, of life arising, of consciousness emerging. And that story, whether we are alone or not, is worth telling, worth living, worth celebrating. The cosmos is vast, ancient, and full of wonder, and we, small as we are, fleeting as we are part of it. We belong here, and that is enough. As the observations of 3i Atlas wind down, as the comet moves beyond the reach of our instruments, as it fades from visibility and returns to the anonymous darkness of interstellar space, we must take stock of what we have learned. Not just the scientific data, not just the measurements and the spectroscopic analyses, but the deeper lessons, the insights that will shape how we approach the next interstellar visitor, and the one after that, and all the ones that will come in the decades and centuries ahead. The first lesson is humility. We began this journey thinking we understood comets, thinking we could predict their behaviour, categorize them, explain them with our models and theories. But 3i Atlas defied our expectations. Its composition was unusual, its behaviour was anomalous, its origin was mysterious, and try as we might, we could not fit it neatly into our existing categories. This forced us to acknowledge the limits of our knowledge, to admit that the universe is more complex, more diverse, more surprising than we had imagined. This humility is essential for science. It is what keeps us honest, what prevents us from becoming dogmatic, what drives us to keep questioning, keep testing, keep refining our understanding. When we encounter something that does not fit our models, we have two choices. We can dismiss it as an error, an anomaly, an exception, or we can take it seriously, use it as an opportunity to expand our models, to deepen our understanding. 3i Atlas has forced us to choose the latter, and that choice will make us better scientists, better thinkers, better explorers. The second lesson is patience. The window to observe 3i Atlas was brief, a few months from discovery to departure, and yet in that short time we mobilized resources across the globe, coordinated observations from dozens of telescopes and spacecraft, analyzed terabytes of data, published papers, held conferences, debated hypotheses. We worked with urgency, with intensity, with the knowledge that this opportunity would not come again. But we also learned that some questions cannot be answered quickly, that some mysteries require time, that some data takes years to fully analyze and understand. The observations of 3i Atlas are complete, but the science is not. For years to come, researchers will pore over the data, looking for patterns, testing theories, refining their conclusions. New techniques will be developed, new instruments will be built, and future scientists will look back at the data from 3i Atlas with fresh eyes, asking questions we have not thought of yet, seeing things we missed. The legacy of 3i Atlas is not just what we learned in 2025, but what we will continue to learn for decades to come. The third lesson is collaboration. The study of 3i Atlas was a truly international effort, involving scientists from dozens of countries, from universities, space agencies, private companies, and amateur astronomy groups. Data was shared openly, results were published in real time, debates were conducted in public forums. This openness, this willingness to collaborate, this spirit of collective inquiry, is one of the great strengths of modern science. It ensures that no single group has a monopoly on knowledge, that multiple perspectives are considered, that errors are caught and corrected quickly. But the collaboration extended beyond science. Governments coordinated their responses, ensuring that observations were prioritized, that spacecraft were redirected, that funding was allocated. The media covered the story with accuracy and nuance, avoiding sensationalism, helping the public understand the significance of the discovery. And the public engaged, asking questions, following the observations, participating in discussions demonstrating that science is not just for experts, but for everyone. The fourth lesson is preparedness. When 3i Atlas was discovered, we were not fully ready. We did not have a dedicated mission to intercept interstellar objects. We did not have protocols in place for rapid response. We did not have the infrastructure to study such objects in the detail we would have liked. But we adapted, we improvised, we made do with the resources we had, and we learned what we need to do better next time. Already, plans are underway to develop new instruments, new missions, new strategies for studying future interstellar visitors. The Comet Interceptor mission, being developed by the European Space Agency, is designed to be on standby, ready to launch quickly to meet a newly discovered comet, whether from the Oort cloud or from interstellar space. Ground-based surveys are being upgraded, with more sensitive detectors, faster processing, and better algorithms for identifying unusual objects. And space agencies are discussing the possibility of a dedicated interstellar object rapid response program, a fleet of small, inexpensive spacecraft that could be launched on short notice to intercept and study these rare visitors. The fifth lesson is philosophical. 3i Atlas has reminded us that the universe is not static, that it is dynamic, interconnected and full of surprises. Objects travel between stars carrying material from one solar system to another, mixing and enriching the chemistry of the galaxy. We are not isolated, not cut off, but part of a vast network of exchange, of flow, of movement. The atoms in our bodies, the molecules in our DNA, may have originated in distant stars, travelled through interstellar space, and been incorporated into our solar system billions of years ago. We are quite literally made of stardust, made of the same material that comprises 3i Atlas, connected to the cosmos in ways that are both physical and profound. This realization changes how we see ourselves. We are not separate from the universe, observers looking in from the outside. We are participants, part of the system, made of the same stuff, governed by the same laws. And this connection, this fundamental unity, suggests that whatever life exists out there, whatever intelligence may have evolved on distant worlds, is not fundamentally alien, not fundamentally other. It is, in some deep and important sense, related to us, part of the same cosmic story, woven from the same threads. And finally, the sixth lesson is hope. Despite the uncertainties, despite the ambiguities, despite the unanswered questions, the story of 3i Atlas is ultimately a story of hope. Hope that we are not alone, that the universe is rich with life and intelligence, that contact is possible, that the future holds wonders we can barely imagine. Hope that humanity can work together, can rise above our divisions, can focus on what unites us rather than what divides us. Hope that our descendants will look back at this moment, at the observation of 3i Atlas, as a turning point, the moment when we truly became a species that looked outward, that reached for the stars, that dared to ask the biggest questions and seek the deepest truths. This hope is not naive. It is not a denial of the challenges we face, the uncertainties we must live with, the risks we must take. It is a recognition that the journey is worth it, that the search is valuable, that the act of exploration, of inquiry, of reaching beyond our current limits, is what makes us human. And that as long as we continue to ask questions, to seek answers, to look up at the night sky with wonder and curiosity, we will continue to grow, to learn, to evolve. 3i Atlas came, it passed, and it is now gone, but its legacy remains. In the data we collected, in the questions we asked, in the debates we had, in the collaborations we formed, in the technologies we developed, and most of all in the sense of possibility, of connection, of belonging to something larger than ourselves. That legacy will shape how we approach the next interstellar visitor, and the one after that, and all the ones yet to come. And it will remind us always that we are part of a universe that is vast, ancient, mysterious, and ultimately inviting. The story of 3i Atlas is not an isolated event. It is a chapter in a larger narrative, a narrative that is still being written, that will continue for centuries, perhaps millennia, as long as humanity continues to explore, to observe, to seek understanding. Because 3i Atlas will not be the last interstellar visitor. There will be others, and each one will be an opportunity, a chance to learn more, to refine our understanding, to answer the questions that 3i Atlas left unresolved. The frequency of interstellar objects passing through our solar system is still uncertain. Based on the 3 confirmed detections in less than a decade, astronomers estimate that such objects pass within the orbit of Jupiter roughly once per year, but many, perhaps most, are too small, too faint, or pass too far away to be detected with current technology. As our instruments improve, as our surveys become more comprehensive, we will detect more of these visitors, and as we do, patterns will emerge. We will learn about the distribution of interstellar objects in the galaxy, about their compositions, about their origins, and we will be ready. The lessons learned from Oumuamua, Tui Borisov and 3i Atlas have informed a new generation of missions and instruments specifically designed to study interstellar objects. Let us look at what is being planned, what is being built, what the future holds for interstellar object science. First, there are the survey telescopes. The Vera C. Rubin Observatory, currently under construction in Chile, will begin operations soon. This telescope, with its enormous field of view and highly sensitive camera, will survey the entire visible sky every few nights, detecting millions of asteroids, comets, and transient events. It is expected to detect interstellar objects much earlier than current surveys, giving scientists more time to plan observations, to redirect spacecraft, to mobilize resources. With Rubin operational, we may detect interstellar objects weeks or even months before they reach their closest approach to the Sun, rather than the days or weeks we have had with recent discoveries. Second, there are the space-based observatories. The James Webb Space Telescope will continue to be a premier instrument for studying interstellar objects, providing detailed spectroscopy and high-resolution imaging. But it will be joined by other missions. The Nancy Grace Roman Space Telescope, scheduled for launch in the coming years, will have a wide field of view and will be capable of detecting faint, fast-moving objects. And there are proposals for dedicated interstellar object monitoring missions, spacecraft positioned at the L2 Lagrange point behind Earth, constantly scanning the sky for new arrivals. Third, there is the Comet Interceptor mission. This mission, developed by the European Space Agency, is designed to be a rapid response system for newly discovered comets. The spacecraft will be placed in a parking orbit, waiting, ready to launch at short notice to intercept a comet as it approaches the Sun. If an interstellar object is detected early enough, Comet Interceptor could be redirected to intercept it, providing the first close-up observations of an interstellar visitor. This would be a game-changer, allowing scientists to study the surface, the nucleus, the outgassing jets, the composition, in far greater detail than is possible with remote observations. Fourth, there are proposals for even more ambitious missions, concepts for interstellar object rendezvous missions, which would not just fly past the object, but match its velocity, travel alongside it, study it for weeks or months. Concepts for sample return missions which would collect material from an interstellar object and bring it back to Earth for analysis in laboratories. These missions are technologically challenging and expensive, but they are not impossible, and as interstellar objects become a regular part of our observational landscape, the case for such missions becomes stronger. And fifth, there is the infrastructure being built on Earth and in space to support rapid analysis and decision-making. International networks of astronomers, coordinated by organizations like the International Astronomical Union and the Minor Planet Center, are developing protocols for rapid notification, data sharing, and coordinated observations. Space agencies are establishing rapid response teams, ready to redirect spacecraft to prioritize observations, to make quick decisions when opportunities arise. And funding agencies are beginning to set aside resources specifically for interstellar object science, recognizing that this is a new and important field that deserves dedicated support. But technology and infrastructure are only part of the story. Equally important is the development of theoretical frameworks, models, and hypotheses that can guide observations and help us interpret what we see. Astronomers are refining their models of how interstellar objects form, how they are ejected from planetary systems, how they travel through the galaxy, and how they interact with the stars and planets they encounter. Chemists and geologists are developing models of how composition varies with formation environment, how surface weathering occurs in interstellar space, how volatiles are lost or gained. And astrobiologists are considering how interstellar objects might carry organic molecules, or even life, from one star system to another, a process called panspermia. All of this work is preparing us for the next visitor, and when it comes, we will be ready. We will detect it earlier, study it more thoroughly, ask better questions, and hopefully get better answers. We will learn not just about the object itself, but about the galaxy, about the processes that shape planetary systems, about the potential for life beyond Earth. And perhaps, just perhaps, one of these future visitors will provide the definitive evidence, the unambiguous signal, the clear indication that we are not alone, that somewhere out there, among the stars, there is another intelligence, another civilization that has reached out, that has sent a message, that is waiting for us to respond. This is not science fiction. This is not fantasy. This is the future we are building step by step, observation by observation, discovery by discovery. The universe is vast, but it is not empty. The cosmos is ancient, but it is not static. And we, humanity, are part of it, explorers in a universe that is full of mysteries, full of possibilities, full of potential for connection and discovery. The next visitor is coming. It might be next year, or in 5 years, or in a decade. But it is coming, and when it arrives, we will be watching, we will be ready, and we will be prepared to learn from it, to be inspired by it, to be changed by it, because that is who we are. We are the species that looks up, that wonders, that explores. We are the ones who refuse to accept boundaries, who push the limits, who dare to ask the biggest questions. And as long as we continue to do that, as long as we continue to reach for the stars, the future is bright. The possibilities are endless, and the story of humanity is still being written. We have reached the end of our journey through the story of 3i Atlas. We have explored its discovery, its characteristics, the observations made by spacecraft and telescopes around the world. We have examined the anomalies, the debates, the secret mobilization, the philosophical implications. We have asked whether it is natural or artificial, whether it is a comet or something more, whether it is a messenger from another civilization or simply a piece of cosmic debris. And we have learned that the answer, at least for now, is uncertain. But uncertainty, as we have discussed, is not failure. It is an invitation to remain curious, to stay open, to continue exploring. The universe does not always give us clear answers. Sometimes it gives us mysteries, questions without resolutions, puzzles that tantalize but do not immediately yield. And these mysteries are valuable because they drive us forward, because they force us to think deeper, to look harder, to imagine more boldly. 3 Atlas has given us such a mystery. We have data, we have measurements, we have observations, but we do not have certainty. We cannot say definitively whether it is natural or artificial. We cannot prove that it is a probe from another civilization, but we also cannot rule it out. And in that ambiguity, in that space between knowing and not knowing, there is room for wonder, for imagination, for hope. This is the calm of the cosmos. It is not the calm of empty space, of silence, of nothing. It is the calm of patience, of acceptance, of recognizing that some questions take time to answer, that some mysteries are meant to be lived with, contemplated, savored, rather than solved immediately. It is the calm that comes from knowing that we are part of something larger, something ancient, something that will continue long after we are gone. As we stand here, at the conclusion of this meditation, let us take a moment to reflect on what it means to be human in a cosmos like this, to be small and yet significant, to be temporary and yet part of a story that is eternal, to be limited in our knowledge and yet unlimited in our curiosity, to be isolated on a single planet and yet connected to the entire universe through the laws of physics, the chemistry of the elements, the shared origin of all matter in the hearts of stars. We are made of stardust. This is not a metaphor. It is a literal fact. The atoms in our bodies, the carbon and oxygen and nitrogen, were forged in the nuclear furnaces of stars that lived and died billions of years ago. Those stars exploded as supernovae, scattering their material across the galaxy. That material, enriched with heavy elements, coalesced into new stars, new planets, new worlds. And on one of those worlds, on a small blue planet orbiting a yellow star in a quiet corner of the Milky Way, that stardust organized itself into cells, into organisms, into life, into consciousness, into us. We are the universe looking at itself. We are the cosmos becoming aware of its own existence. And when we look up at the night sky, when we study objects like 3i Atlas, when we ask questions about where we came from and whether we are alone, we are not separate from the universe. We are the universe asking those questions of itself. This perspective, this cosmic perspective, is humbling and empowering in equal measure. It is humbling because it reminds us of our smallness, our fragility, our dependence on a thin layer of atmosphere, on a moderate temperature, on liquid water, on the delicate balance of forces that makes life possible. It is empowering because it reminds us of our connection, our participation, our belonging. We are not outsiders, observers peering in at a universe that is alien and indifferent. We are insiders, part of the system, woven into the fabric of reality. And this belonging, this sense of being part of the cosmos, is the foundation of the calm we seek. It is a calm that comes from knowing that we are not lost, not adrift, not abandoned in a meaningless void. We are home, not just on Earth, but in the universe. The cosmos is our home, in the deepest and most profound sense. And every object we observe, every star we study, every mystery we encounter is part of that home, part of our extended family, part of the story that we share. 3 Atlas, whether it is a comet or a probe, whether it is natural or artificial, is part of that story. It came from the same galaxy, travelled through the same space, felt the same forces of gravity and radiation that shape all matter, and for a brief moment its path intersected ours. We saw it, studied it, wondered about it, and in doing so, we connected with it, acknowledged it, honoured it as a fellow traveller in the cosmos. And now it is gone, receding into the darkness, continuing its journey. But the connection remains. The data we collected, the questions we asked, the insights we gained, these are not lost. They are part of our collective knowledge, part of the human story, part of the legacy we leave for future generations. As we close this meditation, let us carry with us the lessons of 3i Atlas, the lesson of humility, of recognizing the limits of our knowledge, the lesson of patience, of accepting that some answers take time, the lesson of collaboration, of working together toward common goals, the lesson of preparedness, of being ready for the next opportunity, the lesson of connection, of seeing ourselves as part of a larger whole, and the lesson of hope, of believing that the future holds wonders we can barely imagine. These lessons are not just about astronomy or science or interstellar objects. They are about how we live our lives, how we relate to each other, how we see our place in the world. They are about cultivating a mindset, a way of being that is open, curious, humble, and hopeful. A mindset that embraces uncertainty, that finds beauty in mystery, that seeks connection, that looks outward with wonder. This is the calm of the cosmos, and it is available to all of us, not just scientists and astronomers, but every person who takes a moment to look up at the night sky, to contemplate the stars, to ask the big questions. It is a calm that comes from perspective, from seeing ourselves in context, from recognizing that we are part of something infinite and eternal. The story of 3i Atlas is over, but the story of humanity's relationship with the cosmos is just beginning. We are at the dawn of a new era, an era in which interstellar objects are no longer theoretical curiosities but regular visitors, an era in which we have the technology to study them, to learn from them, to be changed by them. An era in which the possibility of contact with other civilizations is not science fiction, but a real and present question that we must grapple with. And as we move forward into this new era, let us do so with the calm of the cosmos. Let us approach the unknown not with fear, but with curiosity. Let us face uncertainty not with anxiety, but with patience. Let us meet the other, whether it is an interstellar object or an alien civilization, not with hostility, but with openness. And let us remember, always, that we belong here, that we are part of the cosmos, and that the cosmos, in its vast and mysterious way, is part of us. The stars are calling. They have always been calling. And now, finally, after millions of years of evolution, after thousands of years of civilization, after centuries of science, we are ready to answer. Not with certainty, not with all the answers, but with questions, with curiosity, with a willingness to explore, to learn, to grow. The Atlas has passed, but the journey continues, the cosmos waits, and we, the children of Earth, the descendants of stardust, the questioners, the explorers, the dreamers, we are here, we are ready, and we are listening. The calm of the cosmos surrounds us, and in that calm we find not emptiness, but fullness. Not silence, but the quiet hum of a universe alive with possibility. Not isolation, but connection. Not an end, but a beginning. Welcome home.